Your statistical education up to this point has emphasized the need for a representative sample as one of the conditions for the use of inferential techniques. A combination of an appropriate sample size and random selection is the best way to get a representative sample. Anything else introduces bias that can make the statistical analysis and the conclusions drawn from it worthless. Let's review the general idea of sampling first. Remember that the word population means all the items of interest, and that it is not just people. We may be interested in all flights that originate at Midway, or all tires in inventory, or all trees in a national forest. Of course, we might be interested in people, so our population also could be all pilots, all professional baseball players, or all students at a particular school. The population should be defined as closely as possible to the true research interest, so it probably takes more words to be precise about exactly what needs to be sampled. For everything but the trees, and maybe even then, there is probably a database that includes quite a lot of information about those items of interest. Your question may in fact be answerable mathematically by simply averaging the heights of the pilots or counting to see if there are more boys or girls in the fourth grade. When you have the appropriate data on all items in the population, you have census data and don't need statistics. However, if that database doesn't include the type of car that the baseball players drive or the favorite brand of shoes for the flight attendants taking off from Midway, sampling gives us a way to make statements about the cars of all baseball players or the shoe preference of all flight attendants without having to take a census of the whole population. A well-selected sample can give us data that are used in combination with probability distributions to make good estimates about what is true in a population. Many interesting research questions apply to populations where it is either too expensive, too time-consuming, or simply impossible to take a census. Email me at beverly.wood@erau.edu if you want to hear what the American Statistical Association has to say about the U.S. Constitution's requirement for a census of all people living in the United States every 10 years. This is a population of trees. We do not have time to count all the cones on all of these trees, so we sample 10 trees. Now the data collection is doable. As long as this is a random sample, we can use the count of cones on these trees to estimate the average number of cones on all the trees. The meaning of the word random in everyday conversation has meanings like this. In the mathematical subject of probability, which is used in inferential statistics, it means that we cannot readily see the pattern, although it exists. In order to depend on the laws of probability to get a representative sample, we need to ensure that the sample is collected randomly. Our goal is to be certain that every item in the population was equally likely to be selected into the sample. The most straightforward way to take a random sample is the simple random sample. The simplicity is in the basic premise of putting all the names in a hat. That works reasonably well as long as there exists a list of all the items in the population that could be printed on slips of paper and put into a container. If you stir the papers and draw one slip of paper for the first item in the sample, then stir and draw again, you will get a fairly representative sample as long as the sample size is large enough. The topic on our next slide. The trouble with that plan is that the populations are often too large for such a procedure. We can approximate the task using computers and their random number generators. Variations on the SRS still retain an element of the name out of a hat, but have some advantages in either the sample selection or the data collection. Usually a matter of saving time, which translates into saving money. When you read about nationally representative samples, it is a near certainty that stratified random sampling has been done to ensure that all geographical parts of the United States have representation. Techniques to avoid are convenience and judgment sampling. No scientific conclusions can be drawn from anything learned from such samples. Yet, they are reported and shared in print, through social media, and many internet news sources. Wise readers look for the sampling methodology to confirm that random sampling were used before making decisions based on statistical inference. One condition for any of the inferential techniques in an introductory stats course is that the population has a normal distribution, or that the sample size is large enough so the central limit theorem will apply to the sampling distribution. We rarely can be certain about the shape of the distribution of a population data, so the large sample size is generally required. How large does it have to be? That depends on what statistic you are going to use and which statistician you ask. Working with means, regression coefficients, or correlations, most textbooks will say that your sample size should be greater than 25 or 30. For proportions, the expected number of items in the category of interest as well as the number of items outside that category both need to be big enough. Again, not all statisticians agree, but it is usually considered to be 5 or 10. Bigger is better? To a point, that's true. Once more, there isn't a hard and fast rule, but there is concern that a huge sample is really just a census with missing data, a whole other world in statistics. Introductory textbooks might mention a ratio of sample size to population that should be the upper limit. Here are two ways to say that the population should be at least 10 times larger than the sample. The key takeaway from this mini lecture is that statistical inference requires a representative sample from which to draw conclusions that apply to a population. To get a representative sample, it must be collected randomly, in the mathematical sense, and be of sufficient size to support the probabilities used in the statistical analysis.